Okay, so far we have looked at this course from a very mechanism-centered approach. And before the class started, I heard David talk to some students behind and say, are you a systems kind of student or are you an application kind of student? And David, you are an application kind of person? And I'm personally a very systems kind of person. Okay, so the world revolves around mechanisms and abstractions for me. Okay, and applications are just things to go and illustrate why these abstractions are so nice. Okay, so that's one viewpoint, and this course is called Distributed Systems. So my philosophy seems consistent with that. And when you take this approach, you say, okay, if you build it, they will come. And who knows what all will come. So here are some things that I've designed the system for. But there may be new things that we can that may also come. And if you build the right platform, you'll discover all these interesting applications that people might want to build. Okay, so when we were talking about web versus non-web, and the web first came in, the applications that are really created weren't dreamt of at that time. Okay, so I think there's a lot of scope for creativity in applications. Okay. But you can also sort of take an application-centered view and say, okay, web is the application of interest, and we go and just focus on it. Okay, or some other set of applications are of interest. And here then you can say, okay, I want to build these applications, and now what do I have in Android or what some other system to go and build these applications? You can say, oh, you can use RPC, you can use threads, you can use monitors. And if you focus on certain applications, maybe, some new abstractions can be discovered by saying, okay, you can do this application this way too. So the discovery happens in the abstractions because that is the unknown. Okay, and what's known is the application. So I want to change hats right now. I'm not that comfortable with this hat, but I do want to change hats and sort of focus on, for a while, the problems rather than the abstractions. Okay. And then through that, maybe devise new abstractions. So then that meets my goal of being a systems guy. Okay. So I'm going to now just give you these 5 classes of applications. I could only fit 5 here. And I'm going to group the first 4 into one group. And the other one, and so what I want you guys to think about and put your application hat on, and I really believe that even if you're not an application person, if you're a systems person, you'll go much further in life if you think of applications, because that's where you'll understand better the limitations of your abstractions also. Okay, so I think it's very good to sort of think of applications. And so the next question I want to sort of pose is, if you look at these examples, based on these examples, let's try to, we can probably interpret what the functionality is in each of these ovals. Let's go and try to figure out why, what the differences are within the group of pink and green, and so within the group of pink, and then what distinguishes the pink ones from the green ones. Okay. So we can try to figure out what is the reason why we have distributed computing. Okay, and here we're trying to provide some remote service. Okay, so you are at some location and you're there. Okay, so that's what Randy said, that you're at a specific computer, and we want some remote service. And the first so I'm actually first distinguishing among the ovals in the pink group. So in the first circle, we're trying to provide a remote service. Okay, it could be remote printing, remote desktop. Here we're trying to, why did you replicate the files? Why not just have the files in one place? And the usual reason is fault tolerance. Okay, so that's one reason why. And so this is kind of contradicting what Nolan said, that you don't really need distribution there, but you're using distribution so that you get some benefit. You could have that file system that's not distributed. Okay, but you're doing it not for performance reasons, but for fault tolerance reasons. Okay, so I always recommend to people, please save your project work, especially in my courses where the assignments are cumulative. Please save it on some cloud storage. Okay, and if you don't, and if you submitted something to us, we can certainly give you back what you submitted to us, and I've done that for students. Because that's the only copy they have, is the one they've submitted in Sakai to us. Okay, and this is collaboration among distributed users. So this is kind of what Randy said, that people are at specific locations, and they need to talk to each other. So and this is again consistent with what Nolan said, that if you're going to have collaboration among these people at separate locations, you need a distributed system to get the function you want. Okay, so it's inherently a distributed system. A remote service also, you can argue that if you could have these services, you could have a printer locally, so you don't need it. But if you're at home and you want to access your desktop, then you inherently need distributed computing. And again, we're not talking of users; we're talking of sensors that are at certain locations. And as Randy said, that we don't want to just put the sensors anywhere. We want to put sensors at specific locations. And if you want them to aggregate data together, then you have to build a distributed system. Okay. And this is for, again, Nolan said, this is for some functionality, speed up you want. And you could do the computation not in a non-distributed fashion or in distributed fashion. And the issue really is performance. Okay. And that's the primary reason. Once you've built a distributed system, once you've gone and built a remote desktop system or a collaborative game, you might go and want speed up. Okay, so you might want to go and farm out your game. And by the way, David said that look, these are mostly data delivery systems. Actually, you could have some server that has the whole game and does a lot of the computation, the AI there. Okay, and so then you would want speed up of that part. And once you've gone and started a computation on different computers, you might want some fault tolerance. You might want some way to get to access what the program is doing remotely. Okay, so I've got this computation that's being done remotely. I might want to that's being done among a bunch of computers. I want to go and access, and see what's happening. I want to monitor the job. Okay, so those become the secondary reasons. And in both cases, we might start with a non-distributed existing program. Okay? And what you would do is that, in the first case, you would build whatever service you want to build by having the program partitioned into different processes. Okay? You can start with that. And so, for instance, you might begin with a printing service that only prints locally, and then you might want to break it up into a part that can be accessed remotely, so that you have more functionality. But you started with a non-distributed existing program. So the function you want to provide cannot exist without a distributed program, but there is a single non-distributed version of the function. Okay. Similarly with collaborative games, you guys can't imagine not involving multiple computers. But when we grew up, they were time-sharing systems, and we had different terminals for the time-sharing systems, and like you guys, we played games. But the processing was all done on one computer. And in fact, you can have one hardware system with two people playing games, and I've seen that in Xerox. You can have multiple mouse attached to the same computer. And I've seen the person who demonstrated this application to me doing basically having two people do tug of war and try to drag an object one way or the other. Okay, so but today collaborative applications tend to be associated. Users tend to have different computers with different autonomous mice and keyboards. Okay. In the case of high performance or computing distribution, you might start with a non-distributed single-threaded program, then go to a non-distributed multi-threaded program. That's what you did from A1 to A2. Okay? And then you might go and decide that you want to have a distributed program where multiple processes do the computation. That's A2 to A3. And you could have gone from A1 to A3 directly, and within the distributed programs, you can have threads like you have in your assignment 3. And you could have gone to you may not have gone first to a non-distributed multi-threaded program. You might have gone to a distributed multi-threaded program directly. Okay. And by the way, so you've seen in your A1 to A3 this evolution. In A4, you see the other kind of evolution. You're going to take this Halloween program, simulation program that is non-distributed, and make it distributed. Okay, so you'll see examples of both. Okay, so that's something that unites both of these categories of systems. And another thing that unites these systems, and something we've talked about earlier, so I'm just going to present it, is that we would have threads in our distributed programs. Now, the threads are used for different purposes. So we've seen that threads reduce blocking, threads reduce deadlocks. So that may be the reason why we would create threads in the first category. Okay. Whereas thread decomposition in the green category is done for speed up. Okay. But still, we are going to end up with threads and processes, and that's why I've spent so much time doing threads in this course. Okay, even though it's on distributed systems. Okay, and we haven't, you've seen some examples of thread decomposition for the word token counting and sum, but the classic example is matrix multiplication, and you could have one row be given to each thread when you have multiple rows, and that thread goes and multiplies the row with all the columns. Or you could have one row be given to a process, and within the process you could have multiple threads that multiplies that row with different columns. Okay, so there's all kinds of techniques to go and do speed up. Okay, and so when I said there's all kinds of techniques, that means that choosing on and inventing these techniques is an algorithmic challenge. So how to parallelize distribute a single thread algorithm is a challenge. How do you do that for sorting? How do you do that for matrix multiplication, which is more direct? And also, when you have, David said that there's data delivery system. Data are important in the first category, and there's the issue of consistency. Okay, so especially when you talk of replicated repositories, that how do you make sure that the data are consistent? And so that's going to be an algorithmic challenge that we are going to face, and that's something we look into in depth later in the course. Okay. Okay, so one way we can reduce the algorithmic challenge, okay, and my research is in collaborative applications, and this is truly important there, is to have a central mediating process. And so you have sort of a hub and spoke architecture, if you will, where the hub is the central process, and then there are these satellites around it. Okay, so try to think why you might, based on what little we've discussed about these applications, why might a mediating process be useful in the first category and in the second category, and we can talk of subcategories within the first category too. And think of your games, think of that you might have played, and think of your A2 and A3 assignments. Okay, why might a central mediating process be useful? Okay, so why do we need a central mediator? As Randy said, for consistency, and imagine two users editing the same Google Doc. In what order should data go? And so far. So Google Docs uses a server, and people, like I said, have gone and tried to create replicated algorithms, but they're hard to prove and hard to get right. Okay, and we need in the second category someone to go and divide the work, but at least someone to go and collect the work also. And so that's and we've seen that in A2 and A3. Okay, that you have a central, in A3 you have a central process, the master process that's giving out work to the slaves and collecting the data from them. Okay, so a central mediator is going to be an important entity in many of these, in both cases, for different reasons. Okay, and the central mediator does go and make the algorithms easier. Okay, you can imagine pure distributed versions in both cases, but they're just harder to get right. And there's also implementation challenge, and you're going to see that in assignment 4. So you have basically a single process observable, let's say this. So you have to take components that were bound together in one process and then go and separate them into different processes. Okay? So you have to basically go and have a distributed separation of concerns. When you're using a single process, you can just say, okay, how do I divide my program into different classes? And you might use the observer pattern if you're good. Okay? Now you got to figure out how to distribute the classes among different processes. Okay? And if you have an observer pattern, then it's easier to go and distribute than if you didn't have modularization at all. Okay? And typically, and we spend so much time on producer-consumer relationship because that is something that occurs again and again, that you start with sort of a single-threaded observable paradigm, you go to a multi-threaded one, then you go to a multi-process one. Okay? And a big challenge in computation distribution also is that somebody has written a complex algorithm, they've got it right, it works on a single thread. How do you get it? How do you go and port it to multiple threads? And can you just do it automatically, completely automatically? Okay. Okay, when you talk about security, the distribution, often the word security comes in the same breath. So let's discuss this a little bit. Which class of applications do you think raise more security issues? We'll call the green group the high-performance computing group. Okay, and the top group, sort of the data coupling group. Somehow the data are being coupled there. Okay, either they're aggregated, or they are replicating. You're replicating data, or you're transferring data to some other. You're getting data from a desktop, or you're giving data to the printer. So they all involve data of some kind. And so which do you think poses more security problems? So in the first category, you have the processes that are communicating. They're on autonomous computers owned by different agents, some of whom may be trusted, some of them who may not be trusted. Okay? So that raises all kinds of security issues. Okay? Whereas in the second category, it will typically be host processors under the control of an authority. And so if you're doing harm, if one computer is doing harm to the other computer, it's just doing harm to itself, okay, to the same authority. And that doesn't have to be the case. I'm just saying this is what the usual thing is. So I did my grad studies at Madison, and there was a guy called Miron Livni there who created a system called Condor. And you guys are going to use later a system called Cybers, this is spelled wrong here, which actually has sort of Condor as part of it. And my first job was at Purdue, and there was a guy called Sam Wagstaff there who was into number crunching and trying to find prime numbers. And in fact, I looked up Wikipedia, and there are some primes named after him. And he used Condor. So Wisconsin was a very systems-oriented place. So there were not that many application people for Miron's system. But at Purdue, Wagstaff was always begging me and other people to give our computers so that he could find new prime numbers. So it is not always the case that you'll just go to, today you can go to Amazon, and those days you couldn't go to Amazon. So you just use Condor to go and have volunteer computers compute things. And even today, try to find extraterrestrial life, people, I don't know whether these sites still exist, but people are requested, people's computers are requested to solve this very hard problem. So usually, security issues are not a big concern in data crunching. And as I mentioned, if you can verify whether something was correct or not, you can always redo the computation. Whereas if you lost your data, you lost your data. Or it's been corrupted and it's corrupted. And so security issues are less of a concern. Okay, here's another question let's go and discuss. So you can talk of the lifetime of a process, how long a process lives. And this is a little fuzzy, but some processes live longer than others. So which category do you think has longer lived processes? The HPC processes or the data consistency processes or sharing? Oh, sorry. I was supposed to have student discussion there. So I'll give you the answer. That's too bad. So in the case of the first category, think of remote printer. It's providing a functionality that the operating system normally provides. And we expect the operating system to persist, not go away with each creation of each process. So we expect the remote printing service to be always available. The longer it's available, the better, right? Replicated repositories, again, if it's, you want the servers that are storing your data to be around, the longer the better. Collaborative applications, well, that depends on the user, but there is no problem-specific lifetime. That depends on the user. Okay, and if you're sensing, again, as long as the sensor around, you're trying to go and keep the application persist. Whereas in the other case, you can terminate after each computation. Now, you could have a server that goes and takes many jobs, like in your assignment 3. You have this, you could first do a token counting problem, then you could do a sum problem, and when the user quits, you finish your execution. But you can terminate after each computation because that is a natural termination point. And the shorter that time, the better. Okay, whereas in the first category, the longer the service lives, the better. So we have relatively short-lived, comparatively. You can terminate, but you don't have to terminate if you have a server that serves multiple computations. So I'm coming to the summary, which is here. Independent long-lived processes, short-lived processes, consistency, speed up. We can have mediating server in both cases. In one case, to provide consistency, or to provide just some remote services like remote printing. And a big issue is division of labor between client and server. You can have, for instance, we're talking the game. The whole game could be hosted on a server, or it could be replicated on different computers where the computations are happening there. And security is a bigger issue in the coupling or consistency category than in high performance. Okay, and I've got 3 minutes left, so let me just give you an example. This is near home. Okay, so you guys have been using the grader program that we've created. And at one time, the grader program was run only by the TAs. Okay, and every TA ran the program. There was no distribution at all. And then we said, hey, let's go and create a grading server, so that students could also go and invoke the grader before they submitted the application, they submitted their code. Okay, and then we said, oh, and this happened, by the way. Those of you who've done 401 with me, you've used the grading server. There, okay, and then when I went to 533, we also used the grading server initially, because I couldn't figure out how to go and run these programs on your computer. The infrastructure I needed was too tight. It was too tight. The separation of concerns was not handled very nicely. So I didn't know how to go and break this up into a component that you could run without having to worry about all the stuff that only exists in the TA's computer. Okay. And then you can imagine, 533 assignments being graded by one process, 401 assignments being graded by another process, and you could also imagine the same classes assignments being done by two different processes. That you could have A2 being done by one process, A3 being done by another process. And we could have different tests being done by different processes. So you guys will see, and you've seen in A3 how long your tests take. So that was a big issue. That's why I spent a long time. It took really a lot of effort to break up my code into in such a way that you could execute things locally. And then you can imagine, so different threads doing different tests. And then these processes also for the same assignment breaking up the task into different processes with threads. You can have a whole tree-like structure. Okay, so this is something that is very concrete that we can all relate to, that shows you the fuzzy line between these two categories. That we started off by trying to provide a service, okay, to people in different locations. So it was in the first category. And then we worried about speed up. And I kind of stopped worrying about this architecture. So this tree structure I'd never built because our classroom computer or greater program computer was so slow that you know, there was not enough cores to ever process multiple threads. And that's why people are all going to great scope today, okay, because they have these machines. But it does show you that, you know, you have this service being provided through clients, and you also have this master-slave relationship to go and improve competition, okay? Okay, so let's stop here. We'll end this section next class, and then we'll go in. We'll do a little bit more on this high-performance computing side, and then I'll release the quizzes, and we'll discuss 2 classes after that. We'll discuss the quizzes. Okay. Okay. So last time we divided into our applications, some of the applications that are presented here, into 2 categories, and one had to do with high performance computation, and the other had not to do with high performance computation. Okay, and we said that certain kinds of issues, and you know, if you can't see it, just listen to me. Okay, if we saw that certain kind of issues are primary in the high performance category, and certain are primary in the other, and what is primary in one category becomes secondary in the other. Okay, so one question that arises here is, why is primary versus secondary an important thing? If both kinds of issues arise in both kinds of applications, what do we gain by saying this is primary in this category and this is primary in that category? And so let's talk about that. So from application point of view, which as David said, firstly, secondary issues may not arise. You know, fault tolerance might not be an issue in certain high performance computing. Okay, so allows you to focus on only primary issues. And when you have limited resources, okay, then you might spend your the 2 people you've hired. You want to make them optimize on performance and forget about fault tolerance because you don't have resources to handle that. Okay, so you'll take a hit on those. And this implies that secondary issues may arise only in exceptional conditions. Okay, when they make sense and when you have the energy, when you have the resources to address them. And if that's the case, then here's the abstraction design principle: make the normal case efficient and easy to program. Okay? No. Yes, it is. Actually, Amdahl's law also is saying something similar. That's true. That's true. Exactly. Amdahl's law, I think, looks only at efficiency, whereas this is also looking at easy to program. So make the normal case efficient and easy to program while making the unusual case possible. Okay, so as when we talked about comparing Java versus Java and Lisp, if you have a large program which requires reusability, then Java is optimized for that because it provides you with object-oriented programming. But if you've got a Hello World program, then something much simpler, scripting language, or even Lisp would probably be preferable. So in either case, they're Turing equivalent, but one is making, one is targeting a particular set of applications. Okay. So let's go and just try to understand this principle better, and through that understand something we've studied better, something that is going to be covered in the exams. So this will be a good exercise. So when we studied monitors, we talked about the various semantics of notify. Okay, and I'm going to argue that these semantics made different judgments about what is the usual case and what is the unusual case. Or let's put it another way. Some semantics were targeted at the usual case and some were not targeted at the usual case. Okay, and we finally chose semantics that were targeted the usual case rather than the unusual case. So go back to think back again at what the various alternatives were for notify. Those of you who've done operating systems, you've seen it multiple times, so you should be deeper in your head. But even the rest of you, we talked about this at great length. Okay, so try to think about how this principle was used in the design of the semantics of notify. What does notify really mean? Okay. So with monitors, we saw the hint semantics. And the usual case, we'll argue, and this is a judgment thing. We really don't, nobody's really done a survey of programs and seen what they do, but you can argue for the usual case. So when a thread is notified, it goes into the urgent queue. That's what happens in hint. And when it next enters the monitor, we expect it to find the condition to proceed to be true. Okay, we don't expect it to have been changed by the notifying thread. That is why we waited for the notifying thread to leave the monitor before the notified thread enters the monitor. That's what we expect. That's our judgment call. Okay, maybe if we did a survey of programs, that's what we'll find. Actually, I'm involved in a project right now where a student, Yi Cheng, some of you might know him, we are going through GitHub code and actually seeing how people use various kinds of constructs. So we might be able to actually figure this out also, whether people actually do this or not. Okay. And the unusual case is that a notified thread goes into the urgent queue, and then when it comes back, it finds the condition to proceed false, and then it goes back into the urgent queue. So we've had this extra thread switch, which we needn't have had, which we wouldn't have had we had the absolute semantics. Okay. So if the notifying thread, for instance, goes and changes the condition, then the notified thread will go and find the condition false. It'll go and do a while. It'll go back to the while, and it'll enter the urgent queue again. So in this case, actually, we've got an extra thread switch. In absolute case, in the usual case, what happens? The notifying thread goes into the urgent queue, so that is prevented from changing the condition to proceed. And notified thread goes into finds the condition to proceed true. That's guaranteed. It re-enters the monitor. It exits the monitor, and then the notifying thread re-enters the monitor. And what is it doing? It's going to just return back. So all it did was re-enter to go back, and so there was unnecessary switch to the monitor, which can often occur which is this kind of switch often involves the kernel and system calls, which are expensive, and also it was an unnecessary thread switch. Why switch from the notifying thread to the notified thread and back to the notifying thread? We could have just gone from the notifying thread to the notified thread. Okay. But in the unusual case, absolute semantics would be better, because now now we avoid the problem that we had with the usual case, with the unusual case in the hint semantics, and we don't, we've gone and made the condition to proceed false, so we've saved on the context switch that would occur with the hint semantics. Okay, so that's a judgment call, and there was, like I said, big debate when this was all coming out. People didn't know how it would be used, and Mesa, the language that I believe came out in '78. The other semantics came out in early '70s. Had more experience, so they went for the hint semantics. Okay. Okay. So let's put on our systems hat for a minute and say that, okay, given that we can we have these two classes of applications, and given that there's different sets of primary and secondary concerns in the two sets, let's now target these two application sets and try to see how can we figure out how can we design abstractions targeted at one or the other set. Okay. Right now, what do we know? We know threads, RPC, and monitors. Okay. These work for both. Okay. So we haven't targeted them at one domain or the other. So let's try to see what we can do for each domain. Okay. And we can try to actually do what Jason was suggesting, which was try to figure out some default semantics for both sets. So let's let our abstractions be so high level that the programmer has to do nothing and gets everything by magic. Okay, let's look at these limits here and see what our limits are. And I've kind of asked this question in previous classes, and nobody's really answered this question perfectly, so I'll just give you the answer. Okay, or nobody's kind of known how to go in to even start answering this question. So let me take the first category, the category of non-high performance computing. Okay, and I've told you guys this before, that when we were looking at RPC, we said, let's try to reduce the distribution awareness. Okay, and I said, you know, there are systems that have totally eliminated distribution awareness. That means you can take not distribution awareness in the class header or the procedure header or the calling method or the called method, but in the whole program. We take a non-distributed program and make it distributed. Completely distributed. I mean, complete lack of awareness. And of course, we won't be able to do everything, but we can probably do something. And this was done at Xerox. And what they did was they took a non-distributed operating system and made it distributed. Okay. So can we support complete automation for some subset of application in each domain? And here's the complete automation slide. So what they did was they made the modules of non-distributed program distributed transparently. Okay, that means some modules could go on one computer, some modules could go on the other computer. There was no replication. It was, for those of you guys who are sort of looking through the slides, I think it's okay. Actually, that's fine. You're not going ahead. I forget. So what they did was they said each module will go and be assigned to some computer, and the registry is kept outside the system. So some registry goes and decides which module goes to which computer. Okay, so it places that, and every time, I'll just show you the text also. So the loader, it contacts the registry to figure out on what computer to load each module. Okay, and it might go and load it on computer 1 or computer 2, and then so we have only sort of one namespace, one instance of each service. We can't handle replication, and so what happens is the calling modules, whenever things are not loaded locally, the runtime automatically goes and looks up the registry and goes and forwards the call to the remote module. Okay, so the caller is unaware, the callee is unaware, the runtime is aware, the loader is aware of where each module is, and whenever the procedure call occurs, and today if the procedure call occurs and the module is not loaded, there's dynamic loading, right, in Java. It's just dynamic loading on steroids. It's not quite dynamic loading. It's you just go and you might dynamically load it on another computer, and then you just forward the call to another computer rather than do it locally. Okay, so this was in fact, and this motivates RPC transparency. So that's for this class of applications that's not high performance. It doesn't do everything, but does something. Okay, we could take a regular operating system and move services, move the printing service somewhere else, move the file system somewhere else, and so there was a very attractive idea actually. Now, in terms of the high performance computing, there has been so much work on parallelizing compilers. Compilers that will take your code, take your for loops, and just parallelize them. and do the iterations concurrently on different computers. Okay? So why can't we just have parallelizing compilers? And the motivation there was concurrent programs are hard to write. We are mere mortals. So let the gods of computer science, the compiler writers, actually do the parallelization. And they'll do a better job because they'll just think very, very hard and just and do it right. Okay. As it turns out, you run into the halting problem. To reason about how something should be parallelized, you should be able to understand what it's doing. And if you don't understand whether if something's going to even halt, you really can't make many inferences on it. So they did some things, but not everything. Okay. So that's a limit to automation. But what we can do is we can say, well, we've seen some abstractions. They are Java abstractions. Java is an imperative language for doing concurrency. Let's go and create declarative abstractions that are closer to the domain that you are targeting. Okay. So that brings up the question: can we support declarative abstraction for some subset of each applications in each domain?